In this lecture, I'd like to talk about the Friedel-Crafts alkylation. And this is a pretty common organic reaction and an obvious example of electrophilic aromatic substitution. It's very similar to its cousin, the Friedel-Crafts acylation, which I'll discuss in the next video. And this variant is slightly less popular than the Friedel-Crafts acylation due to a couple of significant limitations, which I'll discuss after I go over the mechanism. And as you can see in the scheme, the blue alkyl group of propyl chloride ends up in the product. So we are alkylating benzene in this case with chloropropane. And actually, any aromatic hydrocarbon would be suitable as a starting material for this reaction. So you could use a monocyclic or polycyclic aromatic hydrocarbon in various states of substitution. And the chemistry generally works. You can also use chlorobutane or chloropentane or virtually any other chloroalkane, and the chemistry will work here. Interestingly enough, this chemistry makes use of a Lewis acid, aluminum trichloride. And aluminum trichloride has an empty p orbital, so it doesn't have a complete octet. And the empty p orbital on the aluminum atom makes it a very Lewis acidic center, so that if there are any lone pairs in neighboring molecules, those lone pairs will very rapidly donate into the empty p orbital on the aluminum atom and form a Lewis acid Lewis base complex. And that's worth noting because it's a significant component of the overall mechanism. So let's have a look at the mechanism. Now, interestingly, if you try to perform this alkylation with just chloropropane, it will not work. There is a delta positive at C1, C1, 2, 3. C1 is electropositive. There is a partial positive there, but it's not nearly electropositive enough for the electrophilic aromatic substitution reaction to work. In other words, we have to find some way of making chloropropane a better electrophile. And we do this by adding a Lewis acid. So here's our aluminum trichloride. And what happens is the lone pair on chlorine donates into the empty p orbital of the aluminum atom, and what you generate is a Lewis acid Lewis base complex. And I'll draw the benzene. And here's what you have. You have this. And now C1 is extremely electropositive. It's a very, very good electrophile. And now benzene will very rapidly come and attack it and displace the chloride here. And what we get is we get our typical sigma complex. And finally, we get rearomatization via deprotonation. And what you get is the desired compound plus AlCl4 or plus H. And you can actually, if you want to be, you can also say plus AlCl3 plus HCl. Either is fine. This is the product though, and this is the general mechanism. Now, it's worth pointing something interesting out. Very often, you might encounter someone propose a mechanism like this. So here is our complex that I just showed below. And there's our delta positive. That's C1, 2, 3. Very often, you might see someone propose this, such that what you get is the carbocation, which is the electrophile that is attacked by benzene. And this is probably not the way this mechanism works. The reason being, a primary carbocation is very unstable. So it's very unlikely for the AlCl4 to leave behind a primary carbocation. Okay, so this is basically not what's happening. In all likelihood, what's happening is precisely the mechanism that I outlined right here. Now, there are a couple of limitations to Friedel-Crafts alkylation, and I'd like to talk about a couple of them. The first and the most significant limitation of this chemistry is as follows. Let's redraw this complex. One of the things that can happen is Hydride from C2 can shift to C1, displace the chloride, and what you now get is a far more stabilized secondary carbocation. A secondary carbocation. And now what happens, of course, is the very same benzene reacts with this cation to give you this sigma complex. And of course, upon rearomatization, the product that you get is this product with the isopropyl group, not with the N-propyl group. So this is a very common side reaction to Friedel-Crafts alkylation because you can get carbocation rearrangements. And so this is one of the reasons that this chemistry tends to be somewhat disfavored. The other interesting thing that can happen with Friedel-Crafts alkylation is that if I draw this chemistry that we're attempting to do in this example, simply the propylation of benzene, B is actually now more reactive than A. Why? Because the propyl group is donating into the ring via inductive effects. And so the electrons, the pi electrons in B are actually slightly more high, they're actually slightly higher in energy than the pi electrons in A. And so what this means is that if you have any AlCl3 and chloropropane remaining, what you can actually find is you can actually get the same Friedel-Crafts alkylation happen again and again. So you can peralkylate, you can dialkylate, you can trialkylate, you can sort of polyalkylate your benzene, and so that you can get a mixture of compounds. In some cases, you can really get a mixture of compounds with Friedel-Crafts alkylation, and this is one of the reasons that the Friedel-Crafts acylation is preferred. And we'll talk about that in the next video.